roll in, just keep them on mute. Yeah, so my name is Anthony Cara. I'm a owner of Business Improvement Group. I'm a consultant, primarily in medical device, but I do tend to get projects in other industries as well. Background is in quality and operations, so to drive improvements in those various areas. Open invitation. Find me on LinkedIn. Reach out. I would love to connect with you. Today, I'm going to be sharing with you instead of the usual PowerPoint presentation. I will be sharing a actual simulation, a live simulation. We're going to go ahead and do a demo in Minitab, where we're going to visualize and quantify alpha and beta errors in variable measures. For those of you that maybe saw the post on LinkedIn, when we have attribute inspection methods in quality management, we're very much accustomed to the 2x2 grid, where we have a true decision or a true situation, and then a decision that's made, either pass or fail. And sorry, I just saw a message pop up. Pass or fail, and with that, you can certainly make the correct decisions of passing or accepting a unit when it should be accepted, and rejecting a unit when it should be rejected. But similarly, you can make different types of errors. You can reject a unit when it should have been accepted. That's your type 1 alpha error. And conversely, you can accept a unit when you should have rejected the unit. And we call that the type 2 or beta error. And again, there's a lot of materials out there, a lot of quality text that will have that diagram, but very rarely, if ever, will you be able to find a diagram like that with variable data. And that's what I'm going to present today. We're going to present that situation where you're actually taking variable measurements and visualizing and quantifying that misclassification, the alpha and beta error. So, as kind of a live demo, I'll be going through things. Unless it's completely urgent, I will ask to hold off questions till the end. We could always go back in the Minitab and redo something if you like. But I do have a kind of sequence that I want to make sure that we're able to get through, so we can demonstrate to everybody a couple of the simulations that we have. So I'm going to start by sharing my screen. All right, so again, this is going to be working, so let's go back and forth a little bit. So first and foremost, I want to set up on this first worksheet. I'm going to set up some calculations. And what we're going to do is we're going to have a part, and that part is going to have some variance associated with it, and with that variance comes standard deviation. Now, the reason why we're doing this is because let's see, in our simulation, we're going to be generating data, randomized data from a distribution, and Minitab doesn't allow you to basically select that distribution on using variances. It looks for standard deviations. So we're going to use a little worksheet just to calculate those standard deviations for us. Then the next thing we're going to do here is the variation that we want to see with respect, percent of total variation that'll be attributed to the measurement system. And then similarly, we'll have the variance and the standard deviation of that measurement variation. All right. So first demo, the first simulation we're going to do, we're going to start off hypothetical. let's say hypothetical, we have a variance component at 90% of my total variation, and I'm going to want my measure to be 10%. First, and through this simulation, not only are we going to be able to see, this demonstration of the alpha and beta error with variable measurements, we're also going to be seeing, some of the functionality in Minitab too. So if you're new to Minitab, or there's some new functions here, so there's some additional learnings, that hopefully you'll be able to walk away with. So the first thing we're going to do is the calculator function. And from here, what we want to do in the store the result, we set up that part standard deviation, and basically the standard deviation with respect to the variation, with the variance, it's the square root. Square root function, and then we go ahead and just select the variance component. And notice here, I generally tend to assign as a formula, and you'll see later on where that comes in handy. Then it allows me to change the variance. If I put variance in, it'll automatically calculate the standard deviation for me again. I know this basically, you see the exciting stuff is coming, but we want to make sure that we have the good simulated data. So next, I'm going to take this 10% of my total variation that I want to see coming from the measurement system, and what we're going to do is, once again, go to the calculator, and in the measurement variance, we're going to put a different equation. Part variance, we're going to divide that by 1 minus the variation that we have, and then go ahead and subtract part variance. And fair enough, right? We get the 10% that we expected. So we have 90%, 10%, and then the standard deviation of that number would be the square root. So for those that just joined, you didn't miss much. We're just setting up some data that we're going to use for our simulations. A little worksheet that I like to have here. And then the next thing we're going to do, we'll create a new worksheet. And that worksheet, we're going to call that Sim1. That's our first simulation that we're first simulation we're going to do. And again, when I talk about these simulations, it's basically using randomized data. Almost like a Monte Carlo type technique, where we're going to use randomized data. We're going to use a deterministic type equation to simulate an outcome, and then we're going to analyze that outcome. So let's say first and foremost, I have a physical part, and that physical part has an actual measurement. So we're going to call that part actual. Then on top of that, we're going to have some measurement variation. Now, in our gauge R&R, we're used to measurement variation having 2 components. You could certainly simulate that and have the repeatability and the reproducibility components. For the sake of this demo, we're going to just keep it simple. We're going to lump those both together into your total variation of your measurement system. And then from there, when you have an actual physical part, and which has variation, and when you have a multiple parts, there's going to be variation among those parts. And then on top of that, you have variation from your measurement method. The observed value that you're going to measure on your part, right? The actual observed value is going to be a summation of those variances of that variation. So to simulate that, what we'll do is we'll generate some variable data. So under calculate, we have randomized data, and we have all these selections that we can choose from. In our demo here, we're going to sample from a normal distribution. And here's where I said before, we can generate as much data as we like and store it in columns. But the inputs that we're looking for is the mean and standard deviation. So before I populate that, I'm going to go ahead back to my worksheet, and I'm going to copy that standard deviation that we generated before. And we're going to generate 10,000 rows of data. They're free. Charge any more for any. So we're going to have 10,000 points of data. and we're going to store that as an actual part. For the first simulation, purely hypothetical, we'll leave the mean as 0, and we will create a standard deviation that would equate to hopefully 90% of the total variation of our measurements. Generate those points, and do the same for the measurement. So I'm going to go to my worksheet and grab my measurement standard deviation. And we'll generate 10,000 points for the measurement variation, standard deviation, and we'll go ahead and generate it. Now, and this is where I mentioned, the Monte Carlo technique, where we're randomly generating some input data, and then we're going to calculate the outcome characteristic equation. And in this particular case, it's very simple. It's going to be the part plus the measurement variation. So go to the calculate, back to the calculator. Very simply put the observation. We're going to take the actual and add the measurement component on top of that. I put that in the wrong spot. Try that one more time. So now we have our data set. Right? Nothing exciting yet, but we're going to do some analyses on these data so that we'll start leading up to some of the principles that are going to guide us towards this variation that we're going to see in our measurements. So first and foremost, let's take a look at the shape of this data. Go ahead and create a graph. The graph will create a histogram. And we're going to create a simple histogram. We're going to look at all 3 variables on the same chart. Select those, and under multiple graphs, we want to overlay them on the same graph. Click OK. And here we have our histogram. Now, a couple things to note on the histogram. The blue that we see behind all 3 is the distribution of actual data parts that we generated. Measurements centered about 0, more or less. And it has a spread plus or minus 3. Then the measurement component would be next. That's the pink chart. We do see also centered about 0 and has a spread of approximately plus or minus 1. And then the yellow we see is very comparable to the blue. Right? So visually, we do see that the overall variation is larger than the measurement variation. At first glance, it looks like it's significantly, not a big difference. But what we can't see is when we add them up, right, randomly, we could see, you get a little hint of it, right? When you follow the tail of the yellow curve, you see that it does seem to extend maybe a little bit outside the blue, but ever so slightly, right? So qualitatively, we're looking at these data, and maybe not seeing a big difference, but nonetheless, we're able to see we are able to see some level of influence that the measurement method may have. That's qualitatively, right? Quantitatively, the next thing we're going to do is under our stats menu, under basic stats, we're going to display some descriptive statistics. And same idea, we're gonna choose all of those variables. And there's only, for the purpose of this simulation, there's only certain statistics that we're going to be interested in. Certainly the mean, the average. Really not concerned with the standard deviations, and I'll explain why in a moment. But we will look at the variance, the min, max, and the range. Deselect everything else. I do leave the number of samples. On occasion, I do make mistakes when I'm doing these simulations, and it's always nice to verify that I have the appropriate amount of samples that I've generated here. So we'll go ahead and generate that. And then here, just a couple points that I want to. First and foremost, for those of you that have worked with me and was within 5 feet of a whiteboard, very often I'll write an equation on the board where the observed variance, right? So sigma squared, subscript observed, right? The observed variance that you see is going to be an addition of, a summation of the observed variation among your parts or from your process, plus the variance of your measurement system. Right? It's additive. It's always additive. And because of that relationship, the variances, that's why I wanted to start off with variances, right? Variances are additive. Standard deviations, not so much, right? So even though we use the standard deviations for a lot of statistical calculations and such, when I want to add things together, we're gonna work in variances. So in this table, we can see that the mean. Again, it's not going to be exactly 0. This is randomly generated data, and may vary slightly, but it's closely centered about a mean of 0. And what I want to point out here is the variance. And again, we chose from a random distribution. It's not quite exact, but if you recall from the first slide, from the first worksheet, we were targeting to have 90% of our variation coming from the part and 10% coming from the measurement method. And as you can see here, it's close. Right? It's for all intents and purposes, 90% of the variation that we've modeled as intended is coming from the part and 10% from the measurement method. Right? Total of we look at them not so much on the measurement, but if we look at the mins and maxes, there's a slight spread, but it's much more apparent in the range. If we look at the original range of 6.9. And it's been expanded to 7.4. So there is a little bit of growth there, right? Which purely comes from the additional variance of the measurement method. Again, these are just basic principles right now. What we're really going to be talking about is the modeling of that alpha and beta error. In order to see that, what we want to do is plot these points on a curve. So to do that, we will go under the stats menu. I like using under regression, not running a full regression, but this fitted line plot is a great tool that it'll perform the regression for you without providing all the statistics. It'll just give you that visual output of a fitted line plot with some of the most pertinent information that you want to see that relationship. So first and foremost, the response. Right, the outcome that we're looking at is that observed part. We want to compare the observed measured values to what the part should have actually been. And I think that's all we need for that. We'll go ahead and click OK. And there are a little bit of statistics here. There's model summary and an ANOVA table. But we're going to go straight to the visualization. And 2 points that I want to note here is one, first and foremost, the fitted line equation. So we could see here that the intercept is, once again, it's not exactly 0, but it's pretty darn close, right? Which is kind of what we expect. If I'm plotting the actual part, what I expect to see versus what I did see, on average, I would expect that to go through 0 with a 1-to-1 relationship. Sure enough, if I look at the slope of the line of this model, it's, for all intents and purposes, it's close to 1, which is what I would expect. If there's a part at -3, that should be at -3. On average, I would expect that value to have a measured value at -3. The other statistic that I want to call attention to here is going to be the R-squared, which is approximately, again, for all intents and purposes, we're going to call this 90%. And the reason why I want to point that out is just the meaning behind that number as well. Interpretation of R-squared, and different folks have kind of different ways of explaining it. The way I like to explain it, try to keep it simple, is that the R-squared represents the variation by my x value. Right? So meaning the overall variation that I'm observing, right? 90% of that can be explained by the variable I have along the x-axis, which in this case is the actual part measurements, right? And again, that aligns with the setup that we have for this model, right? We set out to say 90% of the total variation we wanted to observe was attributed to the part, and then 10% would be the measurement on top of that. And this regression demonstrates that as well. Okay? That is kind of the gist of what we're going to do when we simulate. So that was just the first simulation, just to show some of the basics, right? Some of those basics about just how variation is additive, how we can plot the observed value versus the actual value to see that linear relationship. But then we could also note the spread about it. This R squared value confirms that, hey, 90% of the variation that we have is attributable to the actual variation among the parts. And then the remaining 10% must be explained by something else. And in this case, we know what that is. It was the measurement method. So with that said, I'm going to go in and I'm going to create another worksheet. We're going to create a second simulation. And we're going to use same variables. We're going to go ahead and almost the same steps. We're going to follow just about the same steps, but in this case, let's put something a little bit more meaning, right? Not something centered about 0 plus or minus measurements and things of that nature. Let's say that we have a shaft that we want the nominal to be 1 inch in diameter with a tolerance of plus or minus 0.05 inches. So we'll go back to that worksheet so that we know what variance or what standard deviation we can use. And I'm going to show you another little trick that we can do. And again, this is great if you want to play these what if scenarios, if you're doing a validation, or if you want to make a process improvement and you want to test, or at least pilot or simulate something before you go ahead and make some changes, is a great way of doing it. So we're going to insert some columns, and the first one is, let's just, what is that tolerance that we're talking about, right? In terms of plus or minus specification. And then the other thing is almost like capability, right? What's the number of standard deviations that that I might want to expect out of this process, right? That at least for my simulation purposes. So we said before that tolerance is going to be plus or minus 0.05 inches. And the standard deviation, for the sake of this demo, let's call it 2. And now from here, what I have to do is I have to calculate what this part variance would be based on this, having 2 standard deviations of this tolerance. I go back to my calculator, and in the part variation, we're now going to do a calculation that we didn't before. We just entered that number, but now we're going to calculate it. And what I want to do is basically take that tolerance. I said that tolerance was going to be 2 standard deviations. And again, since that would give me total standard deviations, right? What I'm going to do is I'm going to square this number. All right, there we go. And sure enough, what do I expect, right? Within my tolerance, 2 standard deviations gives me 0.025, right? Half of that tolerance band. 2 standard deviations within the tolerance, so half of that would 0.25. Now, because we set up before with the calculations, we set up everything with equations. Everything else took care of itself for us, right? We only changed this part variation, part variance, and standard deviation was recalculated. We still want to go with the same model of 10% of my total measurement comes from, my total variation comes from my measurement system. And then these variances were calculated for us. So we're going to start with part again, like we did before. Copy that, come over to Simulation 2 tab, and we're going to go back to the calculation, random data, And from a normal distribution, again, we'll do 10,000 points. They're still free. And here, I'm going to generate that data in part. Now, here, I said that the nominal value for my shaft should be 1 inch. And that standard deviation that would be within 2 sigma for us would be at 0.025. Go ahead and generate those points. Go back to my worksheet, and then we mark off the standard deviation that I would expect from my measurement system in this scenario. And we're going to go ahead and generate that again. And this time I'm going to store that in measurement variation. And what I'm going to do is set the mean equal to 0. And the reason why is we're just looking for the relative variation, if you will, that we would see from our measurement system. We're going to generate that variation that we would see, and then we're going to superimpose that on top of the part, the actual part, to get the observed variance, right? So we don't want to add any bias, right, if you will. If there was mean to this, that would indicate bias in our measurement system, which is not necessarily something that we're going to cover in this demo. We're looking purely at the variation or the precision of the measurement and what impact that has on our alpha and beta error. Go ahead and generate that data. And last but not least, sorry, we're not going to generate random data. We're going to go to the calculator, and we're going to see that our observed part is equal to the actual plus measurement variation. I'm going to click OK, and we're going to go through the same steps. So first and foremost, we'll create a graph with the histogram. And we're going to go with a simple histogram. And this time we're not going to graph the measurement variation. We already saw that before. Plus, what's going to end up happening is, since the measurement variation was centered about 0, we're going to have a distribution way off to the left, and then we'll have another. I do want to show, as we did before, any variation that we see before and after the actual versus the observed. And very similarly that we saw before, visually we could see a little bit of influence, right? There is the blue curve behind, and as we start going outward from the center, which I can also note is approximately 1 inch, but as I start going outward, we start seeing that the red bars maybe expand out a little bit beyond the blue bars. Once again, qualitatively, it looks as if, yes, the measurement probably had some influence on that, but we want to know for sure quantitatively. So much like we did in the last simulation, we're going to go ahead and do basic statistics, display the descriptive statistics. And the great thing about Minitab is once you set up the preferences from previous, they stay, right? So we'll go ahead and we'll grab these same variables. The same statistics will be displayed. And again, if we're looking at if we start off with first the mean, right? So we see that the mean, that's pretty, can't get much better than that, right? Even in simulations, right? So that's, for all intents and purposes, we are centered about 1. And what I want to show here is again, look at the relative variances, right? Not the actual values, but if we see here that I compare to the final, this is, for all intents and purposes, let's call that 70 versus 700. So once again, we do have a measurement system where 10% of the variation is going to be attributable to measurement variation, and the other 90% from the parts that we can look at the mins and maxes as well, but once again, if we look at the ranges, in this particular case, so, and again, this is simulation, it's interesting that the overall range was actually slightly tighter. So nonetheless, there's still going to be variation. We're still going to see it. Truth be told, we'll still see where the alpha and beta are. And in order to do that, right, I feel like everything's building up to this next chart that we're going to show. We're going to go back to the regression, create our fitted line plot. And once again, we're going to plot the observed measurement, the part measurements, versus what the theoretical actual part should have been, would have there been no measurement system variation. Go ahead and click OK. And same idea. We're going to have some statistics there, and then we're going to have our beautiful graph. And this is where we're going to do a little bit more analysis than we did in the first one. Let's just check a couple things out first. First and foremost, I'm going to check that intercept to make sure that there's no potential bias or linearity issues, right? So does, for all intents and purposes, go through 0? And again, the slope of the line, for all intents and purposes, is 1. So we have that relationship. And again, for the sake of this simulation, I was wondering, what if I had a measurement method that would take up 10% of my total observed variation, and again, part can be attributed to 90% from my R-squared value. So what I intended to model checks out. Now comes the the visualization of the error. So in order to do that, on Minitab, I can put reference lines, and we do that by doing a right-click, add reference lines. And I said earlier that our specification was 1 inch plus or minus 0.05 inches, which means that my lower specification is 0.095 and the upper specification is 1.05. Those are my limits, and I will plot that on both axes because I have an actual and an observed values that I want to map to one another. Much like we mapped on the linear line, we're going to do that on the specification lines as well. All right, so I opened up a little earlier saying if this was an attribute method, right, we visualized the idea of measurement error with a 2x2 grid. What was the truth versus what did we decide? In variable methods, we end up with a 3x3 grid. There are 9 regions that we need to look at here. And it's within those regions that we're going to identify, visualize, this is where alpha and beta error are. And furthermore, you'll get to visually see to what extent. So let's start on the lower spec, right? Let's say we're measuring parts. And as we're measuring parts, we get values that are below the lower specification, right? So we're getting values, we're in this region here, we're observing values that are less than 0.9. And as we go across this axis, what we see here is that indeed there were some actual parts. Every blue dot in this quadrant corresponds to an actual part that should have measured less than 0.95. And we indeed observed a value less than 0.9. This is a correct decision. We would reject these parts. And this is where we made a correct decision to reject parts that were below specification. So all of these points that may have fallen in here would be the correct decision. If I continue along the x-axis now, what happens is these are parts that I would have rejected because they were below, I observed a value less than 0.95, less than the specification limit. So I would choose to reject these. However, in actuality, those parts were truly acceptable. If it wasn't for the measurement variation, those parts would have been accepted because they actually fall between 9.5 and 1.5. So every blue dot in this corner here, would be misclassified as a reject when it should have been accepted. Okay? That is in the attribute method, we would call that in doing inspections, we would call that a type 1 error or alpha error. false alarm or the producer's risk, right? We call that the producer's risk because the producer is the one that's, and I get this argument, right? Well, the producer has all the risk. I agree, right? They are responsible, but in this particular case, the producer is taking the direct risk because we're taking perfectly sellable product and discarding it, throwing it away. So it is a financial risk for the producer for units that would be measured, misclassified in this region. And then as we continue over, there's nothing really in this region. We'll talk about that later. So let's say, well, we found some parts here that actually they're above 0.9. So we're gonna now analyze qualitatively within this region 0.95 to 1.05. And as we go across, right away we have an issue, right? These are things that we would have accepted because measured values were between 0.95 and 1.05. We would choose to accept these parts. And when we see these parts over here, in actuality, they should have been rejected. Because in actuality, in truth, they were less than 0.95. They were under specification, but we accepted them. That's our beta error. So that's our type 2 beta error. Escape if something got past our inspection, or the consumer's risk, right? And it's consumer's risk because now the consumer is going to receive a part or product that is outside of specification. So down here, it was our alpha risk, and then up here was our beta risk. Then we get into this region here, right, where I'm saying that it's between 0.95 and 1.05. And in actuality, it should have been between 0.95 and 1.05. So this is the region, every point that you see in this region, this is where we made the proper decision to accept those units. As I continue once again along the x-axis, we get into this region where I should have rejected these because they were over the upper specification limit. But once again, because my measured value was between 0.95 and 1.05, I misclassified these and I have accepted these when I should have rejected. So once again, I have my beta error. Error in this sector, beta error in this sector. And last but not least, if I go up top, nothing in this corner, we'll come back to that in a moment. But then when I come over here, these are measured values where I'm making a decision and an observation that these are out of specification on the high side. So I would choose to reject these, but because in actuality they fall between 0.95 and 1.5, making a misclassification of rejecting these when they should have been accepted or could have been accepted. So again, much like we had the alpha error down here, we visualize the alpha error. And last but not least, we come over to this quadrant. We observe them to be out of specification on the high side. They indeed were out specification. We reject them correctly, right? We made the correct decision, no misclassification. So in summary, along this diagonal, these three sectors are correct decisions. Right? Whether two far ends, it's the correct decision to reject. In the middle here, it's the correct decision to accept. Our alpha error is going to be in the top and bottom center sections. This is where we make the misclassification of rejecting something, would have accepted it. And then these two edges on the side here, these are the two regions that visualize our beta error, where we accepted something that we should have rejected. The last two that I didn't talk too much before, in our simulation, we don't see any data points in there, right? So there's nothing to talk about. But if you think about, right, if you were to see data points in there, what does that mean? And what that means is your variation is so wide, your measurement variation is so wide that, you can have parts that, on this side here, right, actual parts that are above specification, and they're showing up as above specification, within specification, lower than specification, right? You have big problems. If you see data points in this region here, or conversely in this region here, you have so much measurement variation that it's a useless method, right? There's no discernment whatsoever. So that's the second simulation. And then the last simulation that I'm hoping to get through with us, third simulation, is an actual gauge R&R. Simulated, right, with similar data. It's in 3, right? And same idea, we're going to have some parts and some actual in the measurement and the observed. But what we're also going to have is, if you've run a gauge R&R before, I need a part ID and I need an operator for each of these. And again, what we're going to do is we're going to use some new tools. We're going to go ahead and create some pattern data. Simple set of numbers. And here we're going to give a part ID. Now, most of you that probably done gauge R&R, is a very common number to use is 10. Grab 10 parts and things of that nature. For the simulation, I'm going to go a little bit different. I'm going to call it 11. And the only reason why is because I'm going to simulate some part numbers, and to get the center plus the same number of samples on either side equally distributed, I need 11. So we're going ahead and we're going to create part numbers 1 through 11, steps of 1. We're going to do that one time, and then we're going to do this whole sequence 6 times. Okay? We're going to have 3 operators, 2 measurements each operator, for a total of, it'll be 66 measurements. So we're going to repeat that 6 times. We're going to do the same thing for the operator, where for the operator we said that there was 3 of them, and what we're going to do is we're going to list that 11 times, right? So the first 11 parts we're going to give the operator 1, then the next 11 operator 2, and so on, and we're going to repeat that sequence 2 times for the 2 replicates. And last but not least, we will generate, and this is where, hey, you might do this when you're doing an actual gauge R&R, but now what we're going to do is instead of putting just measured values in here, we're going to simulate some values. And these are going to be fixed. We're not going to come from a distribution. What we're going to say is the actual part now is going to range anywhere from 0.9 to 1.1 in steps of 0.02. And we're going to list each value 1 time because it's going to align with the 1 through 11, and we're going to repeat that 6 times. Okay. All right. Now, same idea, and again, what we're going to do here is we're going to generate some random data for the measurement variation. Because we do that, we're not going to be able to discern between operators. It's going to be so it's going to show up more as repeatability than reproducibility. But for the sake of this demo, that's okay. Generate, let's see, random data, a normal distribution, and it's the same, right? It's the same distribution that we're looking at before because it's the same parts. We're going to go ahead and generate that data. Last but not least, calculate the sum. Again, it's going to be the observed parts is the part actual plus the variation. All right, now instead of doing all the graphical analysis and such, this is now a gauge R&R, right? What would my gauge R&R tell me for a method like this, where 10% of my variation is coming from the measurement? So here we'll go stats, quality tools, gauge study. We're going to do a cross study. These are shafts, so each operator can inevitably measure the same part. Part numbers of the part, the operator is the operator. The measurement data now is going to be our observed data, not the actual, but the observed data. We have the variation on top of that. Under options, I've seen some places use 5.15. Most places use 6. We'll stick with the default 6 for now. And the lower specification, as we mentioned before, is 0.95 to 1. And then you want to make sure that this box is checked, the display probabilities of misclassification. Go ahead and click OK. And All right, so same idea, right? We do get some statistical tables that show up, but what we're going to want to jump to is the gauge R&R itself. And here we see, once again, it's close, it's not exact, but we see that the total gauge R&R that was observed in this study was 12%, right? We superimposed 10% measurement variation, it's showing up as 12% in the gauge R&R. And but when compared to the tolerance that I have here, it's 48. Again, different companies use different standards, and they have different requirements and such. But think about your own company and what your procedures deem as an acceptable, acceptance criteria and what's not. But this would be one that's 10% of your total variation attributed to measurement variation. This is what you would see. And the other two bits is the quantification, right? So in previously we visualized where alpha and beta, what does that mean? Here we're seeing the quantification. Right? So the joint probability, this is if I have a measurement method that I'm doing in process and I'm randomly taking parts off of the production line and I'm taking measurements, these are the probabilities of misclassification, right? So randomly selected part is bad but accepted, right? So that's our beta error, where I accept a bad part, 2.7%. And then conversely, I could have a randomly selected part that was good, but I misclassified it as a reject, right? That's my alpha error. That's 0.3. And again, we're gonna have a graph that's now going to tie this analytical, this quantification. We're going to create one more of those graphs so that we can see what that means visually as well. But before I do that, the last one I want to point out is this conditional probability. This is where you have known, right? This is a known good part or a known bad part, and you still misclassify. And those percentages tend to be a little bit higher. So that's all we want to look for now. As far as, again, this isn't full gauge R&R, but for the sake of this simulation and this talk, this is the quantification, right? How we can quantify that error. If I want to visualize it, I can do something similar. Now, instead of doing a regression analysis, because of the way we distributed the parts, right, that R squared value isn't going to have as much value as it did before. But what we can do is get the same impact from a graphical scatter plot. So we can do the same thing. We can still put a regression line in there. And again, the y variable, I want the observed part value, and I want to compare that to the actual part value. Go ahead and click OK. And as we did before, we'll go ahead and open up this chart and add our reference lines. Five and 1.5. 1.5. And there we go. So here, visually, what does that look like? Remember where the alpha and beta regions are. Let's start with the alpha. The alpha regions, this one down here, this one up here. If I look down below, I don't see any points that really that are in this region. At this point, that's kind of close. But the center of it still looks like within specification. But I do have 3 points here, right? So I have 3 points here. These are misclassifications, right? These are parts that, on average, they should have fallen in here, but 3 times, even in my gauge study, even in my gauge R&R, I've and again, we typically don't do this in a gauge R&R. Most gauge R&Rs, we're just taking the variable measurement and we're, I'll say blindly, just pressing the buttons in Minitab and getting values. But if this was an attribute method, right, we would have failed because we misclassified those parts, right? So these parts got misclassified, and 3 of them out of a total of 66. If you take out a calculator, it's going to be close to 3%, right? So, so here, right, what was calculated as an estimated probability, joint probability of misclassification, we've even seen demonstrated in our gauge study. Now, the beta error in this particular case, and again, you run this simulation a couple times, you'll get different results. In this case, I don't see any here. And then I do have this one point, a majority of the point is over. So I have 1 point beta error, right, demonstrated in my gauge study. And again, if this was a gauge R&R, I might have went ahead and just calculated the values and came up with some number. And if my procedure told me that it was an acceptable number, I would have passed. But we can see here that if this was an attribute method, if I was doing an attribute test method validation, and I wasn't looking for a variable measurement, I just said, okay, here's some good parts, here's some bad parts. Can you tell me if they're, can you discern between good and bad? We would have missed this one, right? Within a sample of 66 measurements, we would have missed one, which for most methods, that's inadequate. So that's it. That's kind of the 3 simulations. I did want to leave some time for questions at the end, and I did see some coming up. So let me switch over to the chat. Stop screen share for a moment. See if I can pull up my chat window. All right, so turning off the cameras. In this example, would we expect the same quantity of parts on the alpha and beta regions? Great question. Not necessarily. It's not necessarily. You're going to see kind of one for one. In this particular case, right, and when we simulated it, it was close, right? When we calculated the probabilities of misclassification, they were very close. They were very close, but it's not always the case. And actually, if I maybe answer a little bit more on that, we go back to the screen share. One thing I want to point out is, those of you that are familiar with variable measurement methods and things like that, there's different techniques, right? If you do have a gauge study that doesn't pass, there's different techniques that we could use, right? Averaging, improve the method, and sometimes it's guard banding, right? Sometimes we implement what we call a guard band, and usually it's to protect the beta error, right? So what happens is if I let me go back to, it's much more apparent on one of these other charts. Let's see, regression analysis. So I had those reference lines before, 0.95 to 1.05, 0.95 to 1.05. Right. So we saw these centers here, and here, if I wanted to adjust for this beta error, right? If I really wanted to make sure that, hey, there's no escapes, I may have to do guard band. What that means is I'm going to put in a tighter acceptance of manufacturing tolerance, if you will, right? So if the product specification is between 0.95 and 1.05, I could put a tighter tolerance in here. I'm just going to make something up. Let's put some reference lines in here. Let's say that I want to go, instead of going plus or minus 0.05, I'll go plus or minus 0.03. So we're going to go 0.97 to 1.03. And what we can see with those new lines, with those manufacturing inspection lines, I now pretty much, almost, right? Here I don't have any, right? There's no beta error here. And for the most part, let's say I've eliminated the beta error, right? So now my beta error is 0 because I tightened the specs up a little bit, right? But what did I do? I traded off, right? I traded off my beta error for my alpha error. So by tightening that, I'm shifting the risk from the consumer to the producer, right? And in some cases, sometimes, right, especially when patient safety is on the line, right, or consumer safety in automotive and what have you, sometimes that's the right call. But yeah, so yeah, in the simulation, the way we had it and we had everything centered, yeah, it would come out even, but that's not always the case. if there's a way. All right, we'll just stop screen share. Back to the questions. All right, so next question, rather than graphically visualizing the alpha beta errors, can we get a percent or number of parts out of 1,000? Yes, we can. Yes, you can absolutely do that. You can do a count of how many times you're outside of this range. You can definitely do those analytics. The visualization is always a nice tool so that there's some meaning. People could put a like a physical meaning behind it. But yeah, absolutely, you could simulate it. Much like when we did the gauge R&R and Minitab gave us the probabilities of misclassification, you could do the simulation and make a similar claim. You could do the simulation with those 10,000 points, count how many of those out of 10% were misclassified as alpha type errors. And you can do that math, and that'll be a good estimate for you as far as what you might expect with that particular scenario. So yes, you can definitely do that. As far as the Minitab version, I currently have Minitab 20. This technique will work on any version that you have. I think all of these tools that we went through are available on all previous versions that I've used. The menus may look and feel a little bit different, but you'll still be able to do that. And yes, that's almost a loaded question here. Most companies call 10% gauge variation good, but there's still a percent risk of being wrong, right? Or misclassification. So what do we do to reduce this risk? And I think I touched upon that a little bit before, right? It's and that's the reason why I put this out, because a lot of times, I can't tell you how many times, folks come to me with a failed study, right? More times than not, we follow the procedures that we're given, right? So our company that we're working for tell us how to do a gauge R&R, right? We're just we're collecting the data and we're pushing the buttons, we get a number, and it either passes or it fails. And if it passes, we just take that on face value and say, okay, well, it's good. But yes, whoever asked this question, right, you're spot on. Your company could say something, there's always a probability of misclassification, right? It's just, is it within your risk level? And if you still determine that it's not within your risk level and you need to take additional action, as I mentioned, there's a couple techniques that you can use. One of them is averaging, right? If take advantage of central limit theorem. You measure the part 3 different times and you take an average, and it should, it'll reduce your that spread of it'll increase your precision. It'll reduce the variation on the measurement method itself. The other technique is guard banding, right? Another technique is improvement method. Well, and that's just it, right? And next question rolls in, right? But 10%, we usually we do nothing and we think that we're okay. And in some cases, maybe it is okay, right? And this is where sometimes too you have to look at beyond just the gauge R&R. Just don't look at one statistic. I say this about a lot of things, right? Just don't go by one statistic, but use it as part of the story. In this example, we even simulated in the first and second simulations. For second simulation, we simulated parts that were going to go beyond, right? It was only a 2 sigma process that we simulated. For that reason, there will be fallout, and the closer you get, right? The closer you get, those errors really only happen near the specification limits, right? So if you don't have a capable process, that measurement variation is going to have more of an impact than if you had a highly capable process, right? If your process variation was very tight, right, and you had 10% variation on that, and you were fairly centered, you would see that when and you could do similar simulations with a much tighter spread, you won't have that error, right? You won't have that misclassification. So you do need to consider your process performance together with your measurement variation. All right, how would you approach a situation where variance is higher than you would typically accept, but there exists no better measurement method for you to utilize? Would you use only CLT, or would you consider the changes to the specification? Great question, right? So Yes, right. Meaning that like all the tools in the toolbox, right? We're engineers, we're here to solve problems. A central limit theorem averaging is one method. Um, if we're ruling out because this is the best method, it's latest tech and that's the best we got. Okay, fine. We'll move on to the next thing. Guard banding, right? Take a cost on that. But then yes, one could always go back and say, hey, is this a true specification? Right? A lot of times I've seen where specifications come almost from thin air, right? Sometimes there was a small sample size and somebody kind of just based on the process said, we believe that we can create within these parts. So yeah, it's perfectly acceptable to challenge the specifications, right? But if you come back and the specifications are the specifications, then you have to work. But yeah, it's always acceptable to challenge the specifications, see where they came from as an option as well. I think we are up on time. Mark or Manuel, I'll pass it back to you to kind of close out. I do want to thank everybody for joining. This is, I enjoyed putting this one together, and I hope you enjoyed. But again, thank you for the invite, Mark, Manuel. I'll pass it back to you.
Yes, thank you very much. It's been very interesting, and unfortunately, it makes us less comfortable in our world at times. But if the truth is truth.
Absolutely right.
So, and again, I want to thank you. Thank everybody for joining. Obviously, look forward in your invites and all the different places where we basically post the next meeting. I am trying to get a tour, so it should be, hopefully will be physical as opposed to virtual. I can't guarantee that, but that's kind of the goal. At least sometime before June. So once again, thank you, and I think everybody enjoyed it.
Excellent. Thank you. Thank you. Have a good night.